Hey, this is Chapter 6, Section 1. So 6.1, when you're labeling your notes, it's the intro to bonding. Starting off, a chemical bond, make sure you get the definition. It is the attractive force between atoms or ions that binds them together as a unit. So when we talk about attractive forces, we are talking about protons and electrons. How do they attract each other? And especially those electrons, if we're talking one atom to another, what's going on with them? And bonds will form in order to increase stability. We've already talked about individual atoms losing and gaining electrons to be more stable, like noble gases. Well, one atom will want to bond with another one if it makes the pair more stable than the two atoms alone. So I need you to put this chart into your notes, and we're going to fill it in. So please take a moment, pause the video, write out this chart, and then we're going to go through each part. You'll fill in the boxes. I'll have some extra explanation along the way too. Starting off, ionic bonds. The bond formation for an ionic bond, electrons are transferred from metal to nonmetal. Electrons are transferred from metal to nonmetal. So as I go through this, I'll make a few notes just as refreshers from the previous couple of chapters. We have talked about metals. Metals want to lose electrons. They form our cations. And then nonmetals typically like to gain electrons to form our anions. So when it says electrons are transferred, metals want to lose, nonmetals want to gain. So that transfer is going to be an electron from the metal to the nonmetal to give you an electrostatic attraction between ions. Because again, you have a cation formed, you have an anion formed, and now there is an electrostatic attraction between your cation and your anion. So the type of structure this creates is called a crystal lattice structure. When we get to section 3, we will go more in depth on this crystal lattice structure. The physical state of ionic compounds, they are generally solids at room temperatures. Since they're solids, they will have high melting points. They are also soluble in water. So if I'm thinking just the normal, you'll see us talk about table salt all of the time. Table salt, Na, which is a metal, chloride, which is a non-metal. They like to get together, and you know that salt is soluble in water. Also, your ionic compounds will conduct electricity, but they have to be in solution or liquid form. So if you take that table salt and you pour some table salt into your hand and stick an electrode in it, it does not conduct electricity. But if you take that same salt that you had just put into your hand and dump it into some water, stir it up, after it dissolves, those ions that it had, those ions go into solution and they will conduct electricity. Heading on up to covalent bonds. Here, it's a little different, whereas in ionic, we transferred electrons. In covalent bonds, we are sharing electrons. And this time, the sharing is going on between two nonmetals. We will treat metalloids like a nonmetal also. So if you're talking about between a metalloid and a nonmetal, it's going to be considered a covalent bond still. So we are sharing electrons instead of transferring. This structure is considered a true molecule. You will hear oftentimes us talk about molecules, molecular geometry, molecular compounds. Anytime you hear that word molecule, you have to think covalent bond. So again, molecules or molecular compounds, we're thinking covalent bond, whereas ionic is really easy. Ionic bonds create ionic compounds. So back under covalent, in general, these are liquid or gases at room temperature. That is in general. Because they are liquid or gas at room temperature, they're going to have a lower melting point and generally not soluble in water. y'all are familiar, especially from biology, all of your sugars contain carbon, hydrogen, oxygen. Well, those three elements are all nonmetals, so they are covalently bonded, but those sugars, will dissolve in water. But in general, covalent compounds do not dissolve in water, and they are not electrical conductors. Some other properties is they typically have an odor associated with them. So, moving on, we're going to look at bond polarity. So, polarity is a new word for you here. Polarity is going to come up over a few different chapters, so might as well get it pat the first time. Most bonds are going to be a blend of ionic and covalent characteristics. It's typically not black or white, but there is going to be a gray area. The difference in electronegativities will determine your bond type. So I'm giving you a copy, if I have not already. I'm going to give you a copy of the electronegativity table that's from the book. Also, these electronegativity values will be posted on Google Classroom. So when we say difference in electronegativity, difference means subtract. Please get this chart in your notes. This one right here especially. There's a lot going on with it, so let's get to explaining. We have two different y-axes. I am going to concentrate on the y-axis that is on the left side first. It's a difference in electronegativity values. The ranges that we are looking at. If the difference between 1.7 and 3.3, we're going to say it's an ionic bond. So 1.7 to 3.3, ionic bond. If the difference between your two elements, electronegativity values, are 0.3 to 1.7, then we're going to say you have a polar covalent bond. And if the difference between them is 0.3 to 0, so 0 to 0.3, we're going to say you have a nonpolar covalent bond. So notice we've even broken our covalent bonds up into two categories, polar and nonpolar, and then you have your ionic. That 1.7 and that 0.3, they are just in general locations. Now, let's look at the other y-axis. The other y-axis is percentage ionic character. Well, ionic character means, okay, how ionic does my bond act? If it does not act ionic at all, then it's got 0% ionic character. So your nonpolar covalent bonds are going to be down there between 0 and 5%. Polar covalent is going to be between 5 and 50% ionic character. So again, not a lot, but if you have over 50% ionic character, then yes, you are going to have an ionic bond, and your bond is going to act very ionically. We could have easily labeled that axis as percentage covalent character, but if we would have, your percentages would have been flipped. You would have had 100% at the bottom, 0% at the top, 50% in the middle, because again, percent covalent character, expect it to be a higher percent towards your nonpolar covalent bond. So again, make sure you have that in your notes and you understand what's going on. So now we're going to go look at our two covalent bonds, starting off with nonpolar covalent. This is where you have electrons that are shared equally. So the picture that you see at the bottom is showing you the nuclei of two different atoms. And you think of their electron clouds as overlapping. So we do have an overlap region right here in the middle. And that overlap region is where you have your sharing of electrons that are being shared equally. So our electron cloud looks very symmetrical. That's why we say it's a balanced electron cloud, because it does look symmetrical. This typically happens with identical atoms because the difference in their electronegativity values would be 0. So if you're looking at your chlorine values, either you have your piece of paper, we're going to do fluorine. If you have your piece of paper or you just remember fluorine is 4, well, if I have two fluorine atoms bonded together, even though that's a very high number, 4 minus 4 is still 0. So fluorine bonded to fluorine is a nonpolar covalent bond, because the electronegativity difference, so electronegativity difference is 0. That means it has 0% ionic character or 100% covalent character. Now, because fluorine falls into that category, I'm hoping you can guess some other elements that would fall into that category. It would be all of your diatomic elements. So if I look at my 7 diatomic elements, there you go. Remember, shaped like a number 7 right over here. Shaped like a number 7, so nitrogen through iodine, and then we've got our hydrogen. So you could take any of these, and in their diatomic state, they're going to be nonpolar covalent. If I were to take oxygen, oxygen's electronegativity value is 3.5. Well, because we have oxygen bonded to oxygen, 3.5 minus 3.5 is still 0. So it is a nonpolar covalent bond. So an equal sharing of electrons within their electron cloud. Make sure you know your 7 diatomic elements. This is not the first time we've talked about them, and it will not be the last. And then we're going to look at polar covalent bonds. And we have a new symbol down there. Those symbols mean partial. It means partial. So we have 2 atoms, and right there in the middle you can see that the electron clouds are overlapping here and here, but it is not an equal overlap in this region. That means one side is going to be partial positive, the other side is going to be partial negative, but how do you know which side is partial positive and which is partial negative? Well, in a polar covalent bond, the electrons are shared unequally because a dipole is created. The dipole is because of that uneven partial charges, even though we are still sharing electrons. The higher electronegative atom has the stronger attraction for electrons. Well, again, the more electronegative your atom, you should remember that electronegativity trends. Electronegativity trends as you move across a period, electronegativity values increase. So we had our big box right up here, but as you move down a group, electronegativity values tend to decrease, and we had our small box right down here. So as you move across the periodic table from hydrogen to chlorine, since that's the example here, our electronegativity values are going to become larger. You could remember that based on the trend, but if you're looking at your table, you have values for chlorine and values for hydrogen, and you can see chlorine is a higher electronegativity value. So your more electronegative atom does have the stronger attraction for the electrons, therefore it gets the partial negative. And then the opposite of that is going to be true. Your less electronegative atom, which is hydrogen in this case, gets the partial positive. So we have polar and nonpolar covalent bonds. Both are sharing electrons, one equally, one unequally. Equal sharing, your diatomic elements fall under there. Unequal sharing, again, between 2 nonmetals, you're going to have a larger difference in electronegativity values. Usually that difference is between 0.3 and 1.7. And then we have some animations going on here between nonpolar, polar, and ionic bonds. So you can watch those animations. Let me go back. You can watch these animations as they go on with the equal sharing, unequal sharing, and then a transfer of electrons, but I have an even cuter video to show you.
Our first lesson is chemical bonding. Chemical bonds are what holds atoms together. A chemical bond is an attraction between atoms that allows the formation of a chemical substance. The electrons that participate in a chemical bond are called valence electrons. These are electrons that are found in an atom's outermost shell. Let's take a look at the types of chemical bonds that can be formed between atoms. An An ionic bond is formed when one of the atoms will lose its electron to the other atom. This results in a positively charged ion, called a cation, and a negatively charged ion, called an anion. Positive and negative attract, and the result is an ionic bond. Covalent chemical bonds involve the sharing of a pair of valence electrons by two atoms. There is also what is called polar covalent bonds. These are covalent bonds in which the sharing of the electron pair is unequal. The result is a bond where the electron pair is displaced toward the more electronegative atom. Thanks for watching, and we'll see you guys next time.
I love that video. I hope it helped with your understanding for ionic and the two types of covalent bonds. So we're going to do a wrap up right here. The numbers that you're going to see in this, I do not think they match up exactly with your electronegativity values on the chart that I gave you, but they will be close and the answers will still be the same nonetheless. So for chlorine, if I asked you what type of bond it's going to have, it says the values for chlorine are 2.83, so you subtract that, find the difference at 0. Because that difference is 0, right down here, it's got to be a nonpolar covalent bond with 0% ionic character. And then HCl, we've already seen it. The values, 2.83 and 2.2. You always take the higher number minus the lower number. We're not trying to get negative answers here. So that's chlorine minus hydrogen. The difference is 0.63, and that one right there with a difference of 0.63 will fall right into this range, so it is polar covalent. And with our last one, NaCl, you should be able to answer that one even without electronegativity values. And the reason why I say that is you should recognize sodium as a metal and chlorine as a nonmetal. Automatically, it does not matter if they fall into the gray area of where ionic and covalent are. We say it's a blend anyways. But a metal and a nonmetal has to be ionic. It cannot be covalent. But we're going to throw the numbers up there with them. Chlorine, again, is 2.83. Sodium, 1.01. The difference is 1.82. This one does fall well within the range of being ionic and over 50% ionic character.